Now I'm going to show you some of our nuclear chemistry. So nuclear chemistry is actually one of the most fun chapters that we have, and it's our last chapter. I can't even believe this. So nuclear medicine, if you've ever had anything with contrast, that's been nuclear medicine. And we're going to talk about nuclear medicine more in the end. We also use nuclear radiation to visualize or test structures in the body to see if they're operating properly. And like I said, we're going to use this. We're going to talk way more about these. Nuclear radiation has also been used to treat diseases because the radiation is what's called ionizing. And ionizing means it can be used to attack, well, unhealthy and healthy tissues. So we're actually going to talk about how it ionizes tissues today and the different types of nuclear medicine. So first, let's talk a tiny bit about the discovery of radioactivity. So it was Henry Becquerel who first figured it out. And he thought that there was a relationship between phosphorescence. And phosphorescence is like, you know, the glow in the dark stickers you might have had as a kid, right? Where if you shine light on them and then you turn the lights off and you can like see them, like maybe your parents put them on the ceiling or something of that sort. That's like phosphorescence. So that it absorbs light and then you turn the light off and then it emits that light. That's phosphorescence. So Becquerel thought there was a relationship between phosphorescence and X-rays. And so he was working with uranium. And he called these things uranic rays. And so he thought that the phosphorescence, again, was linked to X-rays. And so what he would do is he would expose uranium crystals to light, and then he would like put it, and then he would actually see kind of the glowing of the uranium. And then he noticed that the X-rays were detected on a photographic plate. So he thought these two were related. Turns out they're not actually related at all. And he amended that later. But he did discover that certain minerals were constantly producing energy, and that energy could penetrate matter. So he would wrap the uranium in like, I don't know if I wrote it on here. I don't even know if I remember what it was. He wrapped it in some kind of paper, and the energy would still get through the paper, and then it would be exposed on this plate. So that's how he knew that it could penetrate matter. And so he figured out that the minerals that produce these rays contained uranium, and the rays were produced even though the mineral was not exposed to outside energy. So what he did eventually is he found out that even if you didn't shine light on the uranium, this energy was still being emitted, right? So that took a little while, a little progression in the research. And he figured out that the X-rays or the uranic rays, that's what they called them, were emitted, but it was not related to the phosphorescence, meaning that it would still show energy on the plate, or you could see the energy transferred on the plate, even if you didn't shine light on it. Okay, which was insane because that means that energy is being produced with no energy in, right? Which kind of goes against many of the things that we have learned. Now to the Curies. So Marie Curie, pretty impressive. She broke down these minerals, used an electroscope to detect the uranic rays and to see what they were coming from. She discovered two elements, radium and polonium. And she is the person who coined the phrase radioactivity. So I don't usually do this, but I want to see, show all windows. Okay, so I want to just show you this little piece here, if I can find it. There we are. Hold on 1 second. And Kate, tell me if you can see this, okay? I'm going to share it right now, and then tell me if you can hear it. Okay, I'm going to play this. It's only like a minute and a half, but this is from the Amazon Prime show called Radioactive, and this is Marie Curie explaining her research. So tell me if you can hear it.
So you take the ore.
Which is a special ore that comes all the way from a mine in Bohemia. And then we use a scientific process to remove the elements we know we can remove and look at what's left.
And what scientific processes might you use?
These are very good questions.
We crush it, which is extremely hard work. Then we boil it, which results in the removal of substance. We add acidic and alkaline solutions to it until only that which is pure remains.
And there's a lot of substance to remove.
And it will be worth it.
It's very exciting.
And why are you looking at uranium in the first place?
Becquerel.
A more than competent scientist.
Becquerel discovered accidentally that uranium salts wrapped in a black cloth left in a drawer left an impression on a photographic plate. And he thought that the uranium was having an unusual chemical reaction with something in the atmosphere. I say it's the element itself.
A very radical thought.
I still don't understand.
Imagine a grape. How do you turn a grape into wine?
Well, you crush it and ferment it.
Yes, so imagine a grape crushes itself, ferments itself, changes its very being. And what if I told you that as the grape turns itself into wine, it releases a powerful surge of energy, power that can make things happen? You'd be excited, am I right?
I think so, yes, I would.
So science is changing. And the very people who are running science are the people who believe the world was flat. And I'm going to prove them wrong, just as Newton did.
Okay, so I know some of you couldn't hear it or see it. I was trying to figure it out. So could some people hear it and see it? I worked on this for like an hour today to try and get Zoom to like agree with my computer. Yeah, some people could. Okay. You only heard it. Okay, so I don't know, like no matter how I try, my Zoom and computer, they hate each other. So what it was is you heard Marie Curie explaining about what her intention was with her research. And so like, it's kind of like she said, like, if when you crushed a grape, all of a sudden it like emitted a crazy amount of energy, she's like, that's what I'm studying. And she actually coined the phrase radioactivity because she discovered both radium and polonium besides uranium that all emitted energy without any energy input in, they were emitting energy. And this is radioactivity. And again, she won 2 Nobel Prizes, so she was a rather smart cookie. One of the first women in France, I think, to even get her doctorate. So, and she named, by the way, polonium, came from her home country was Poland. And radium, because radium had so much radioactivity, that's why she called it radium. No surprise to anyone, both her and her husband died from cancer from radioactivity. Of course, they didn't know that back then. Okay, so other properties of radioactivity, and we're going to talk about these. Radioactive rays can ionize matter. And so what ionizing radiation is so it's an energetic radiation and it interacts with molecules. These molecules can be in your body, anywhere, any kind of living tissue. And if the molecules are a living thing, the energetic radiation can damage chemical reactions that occur in the molecules or the DNA of the molecules themselves. And they can either kill the cells or they can make them start acting like wonky, like reproducing at really weird rates or things of that sort. And that's why radiation can cause cancer, right? Because cancer is the out of control replication of the wrong kind of cell. So it causes uncharged matter to become charged. Geiger counters are these things that like actually click every time. It's really hard for me to explain one unless you've actually seen one. When I was in graduate school, we actually worked on just for an experiment. We had to go work with some radioactivity and we had to wear Geiger counters. And it was actually kind of cool to hear the clicking every time we had too much radiation near us. So radioactive rays, they have really high energy. They can penetrate matter, and there's different types of radiation. And we're going to talk about how different types of radiation can penetrate different types of matter. It also causes phosphorescent chemicals to glow. And we talked about that a little bit. So again, radioactivity, it's the release of tiny high energy particles or gamma rays. And we're going to define these in a minute. And these particles are ejected from the nucleus. So this is very different than everything you've ever talked about in chemistry before. We are changing the nucleus, right? When we're talking about radioactivity, we're changing the nucleus. So we have different types of radioactive decay. So here's kind of what we're going to talk about today. We're going to talk about alpha rays, beta rays, gamma rays, and then we're going to talk about something called electron capture and positrons, which, okay. let's go through all these individually first, and then we're going to spend more time on them. So an alpha ray has a charge of +2 and a mass of 4 AMU. It's the same thing as a helium nucleus. A beta is kind of like an electron. Gamma's pure energy. Remember when you learned the electromagnetic spectrum in 219, like gamma rays? Incredible Hulk, those are gamma rays. Okay, now positrons are like the opposite of an electron. So we're going to be talking about some things today, and you're going to be like, wait, how does that happen? Welcome to nuclear chemistry. And then we have electron capture, which I think is the absolute coolest one, where an unstable nuclei will actually capture an inner electron and then create a neutron. It's kind of cool. And we'll talk about that one too. Okay, so first, let's talk about the penetrating ability of radioactive rays. So we're really going to talk about alpha, beta, gamma here. So you have an alpha ray, which can be stopped by like a piece of paper. Really easy to stop. Then you have a beta. Now betas, that's going to be like a big piece of wood or like a lead vest. And then you have gamma. Gamma is like a foot of concrete, right? Or maybe a couple feet of concrete, or like 10 inches of lead. Gamma, very penetrating. And we're going to talk about what it means to be penetrating radioactive rays. Okay, so we need to establish kind of a baseline about the nucleus. So things we know that the nucleus is a very small volume compared to the atom, right? It's 99.9% of the mass is in the nucleus, right? I always use the example of like if the nucleus was a pin on the pitching mound at Angel Stadium, that was 99% of the mass of the nucleus was up on the pitching mound at Angel Stadium. The rest of Angel Stadium would be where the electrons are. Hence, atoms are mostly empty space, right? So the nucleus is very, very dense. And in the nucleus are protons and neutrons, right? And so we call the particles that make up the nucleus, we call them nucleons. So nucleons are particles that make up the nucleus in general. Okay, so we're going to quick review about our mass numbers and atomic numbers because we're going to be using them. So we know that the atomic number, right, that's the number of protons. The mass number, right, that's the number of protons and neutrons, right? Isotopes can have different neutrons, right? That's what an isotope is, like carbon, 14 carbon, 13 carbon, 12. Isotopes, right? Same number of protons, different mass numbers. These are protons plus neutrons, right? Isotopes. So isotopes, again, are identified by their mass number. The mass number is protons plus neutrons. So this would be, we might write this carbon 14, or we might write this one carbon 12. These are isotopes. So we're going to use this format to talk about nuclear equations now. Okay. So again, we get the number of neutrons by subtracting the atomic number from the mass number, if you're wondering, by the way, which again, we all did this in 209, and I'm sure we probably did a little bit of this in 219, right? To get the neutrons, all you do is subtract, right? That's going to give us the number of neutrons. We're going to be doing the same thing. We're just going to be redefining some things. So the nucleus of the isotope is called a nuclide. So a nuclide is the nucleus of an isotope. Less than 10% of the known nuclides are non-radioactive. Most are radionuclides or nuclides. And I always call it nucleides, but it's supposed to be nuclide. Someday I'll get it. So each nuclide is identified by a symbol, right? And this again is kind of the symbols that we're going to use. So the mass number again, protons plus neutrons here, protons here. And if you're like, I know, we're going to be using it a lot. Okay, so again, what is radioactivity specifically? It's the spontaneous decomposition of a nucleus into smaller nuclei. So we have a couple different kinds. We're going to talk about radioactive decay. We say that radioactive nuclei are unstable. So when they decompose or when they emit energy or emit particles, what they're doing is they're trying to become more stable. So they're trying to stabilize their nucleus. So their nucleus is unstable. And to try and get it stable, they're either going to emit energy or particles or both to try to get to a more stable arrangement of protons and neutrons. And we'll talk more about that next week. Okay, so we have the parent nuclide, and then we have the daughter. So the parent's what it starts with, the daughter's where it ends up with. And so all nuclides with 84 or more protons are radioactive. So you go ahead, take a look at your periodic table, which I know if I move this, you can't see because I disappear or it disappears. So polonium is the first. So polonium, all of these are radioactive. And again, we're going to talk about how and what they do. All right, so remember I told you those nuclear symbols? Here are the nuclear symbols that we're going to be using. It's the same that we had before. We're just going to redefine certain things. So a proton, right? So remember, I'm just going to put this right here. This is protons plus neutrons. And this is protons. It kind of will help you because your brain's going to be like, wait, no, I don't think so, right? So if it's one proton, there's a 1, 1. That's how we write a proton. A hydrogen 1 nucleus, or we just write P for proton. A neutron, again, 1 neutron, no protons, no protons. So 1, 0, that's a neutron. An electron, seeing that electron, it's a little stretch here, right? So an electron, we write it like this, right? And we'll talk about why. An alpha particle is just a 4-2 helium nucleus, right? So if you look at helium on the periodic table, right, it's about, the mass number is close to 4 and the atomic number is 2. So it's, you can either, this is the same as this, right? They're the same, they're completely interchangeable. Now a beta particle, which is an electron, basically, you can either write this or this. This is showing the emission of an electron. A positron, which is the opposite of an electron, which again, you're like, wait, what, huh? Okay, so you can either, right? So here's the negative, here's a regular electron, here's a positron, it's the opposite. And again, you can write it like this or this also. If they're in the same box, they are equivalent. So you should get used to seeing them both ways. Okay, now, let's talk about when these are emitted and how they apply to radioactivity. So transmutation. So Rutherford discovered transmutation, and he discovered that a radioactive process, what happens is the elements of one element, the atoms of one element are changed into atoms of a different element. So remember how you learned in 209 and 219 that protons never change, right? And a proton is the element's identity. Well, in nuclear chemistry, the protons are always changing, right? So we're literally changing one element into another element. And what's getting emitted is energy or matter or both. And this shows that Dalton's atomic theory doesn't work for nuclear chemistry, right? It only works for chemical reactions. It does not work for nuclear reactions. Because for one element to change into another element, the number of protons must change, right? And that's exactly what we're going to be talking about. And we're going to be changing a bunch of protons here. So just a quick reminder, difference between a chemical process and now we're going to go to a nuclear process, right? So we know chemical reactions. We've talked to you a semester, a year and a half, you've been in chemical reactions, right? This is changes in the electron structure, losing, gaining, sharing electrons, right? We're not changing protons, we're not changing neutrons in chemical reactions. Chemical reactions is really the study of the movement of electrons, right? Everyone's trying to obtain those noble gas configurations and lose, gain, borrow, steal electrons so they can get there. With nuclear chemistry, we are talking about protons in the nucleus. So we're changing the structure of the nucleus itself. We are not talking about electrons at all. We're talking about protons and neutrons. And so in chemical reactions, I always talk about how the electrons are beg, borrow, steal, share in order to get to a lower energy, right? So they're more stable. And in nuclear reactions, they're losing or giving away or sometimes capturing pieces of their nucleus, and we'll talk about it in just a second, to try and get a more stable nucleus. So that's the whole goal. In both cases, the whole goal is stability. They're trying to be stable. Okay, so how do we write these equations with nuclear equations? They're very similar to chemical equations where everything has to balance. But in this case, we're balancing protons and neutrons and, well, sometimes electrons. And so we write it just like we did before. So here's like the parent. So for example, here's uranium, right? Here's uranium-238. And you can see here, it's going to turn into thorium-234. And then it's going to emit, this is an alpha particle. Now, if you look at this, 238 is the same as 234 plus 4, right? 238 here, it's 238 here. So it has to equal. You look at 92, 92 equals 90 plus 2. So this is 92, this is 92. So in nuclear reactions, it has to be equal, just like we have been doing in chemical reactions. They just look a little different. Okay, so let's talk about alpha emission first. So alpha emission, again, is called an alpha particle. An alpha particle is a helium nucleus, which is written like this and also just written like that, right? All of these things mean alpha. So it's the most ionizing, which means it can make the most amount of damage because it's so massive, right? It's a 4-2 helium nucleus. It's so massive, but it's the least penetrating. Okay, so how can I explain this? Okay, think of traffic. An alpha particle would be like a semi-truck, right? You get like a semi-truck, if it gets to you, it's going to do some serious damage, right? But think of this. So an alpha particle is the most massive. It has the most potential to interact and damage other things, right? It's like a semi-truck. It can wreak complete havoc. It has the highest ionizing power, right? So the most potential to hurt or damage things means the greater the ionizing power is. But it has the lowest penetrating power. So because it's so big, anything can stop it, really. Think of like if you were in a traffic jam and the semi-truck was trying to weave in and out of the lanes to get out of the traffic jam. Semi-truck can't go anywhere. It's easily stopped. Alpha particles are easily stopped, right? So therefore, if an alpha particle is outside of your body, nothing's really going to happen because you can stop an alpha particle with a piece of paper, right? So you can have the semi-truck coming, but paper is going to stop an alpha particle. But if that alpha particle gets in your body, it's going to ravage it, right? Because it is the greatest ionizing potential or the highest ionizing power, which means that once it does get in contact with a cell, it can create a lot of damage. So outside of the body, alpha particles are like, meh. Inside the body, very dangerous. But again, they're stopped by a piece of paper. So our skin stops alpha particles. Okay, so now, when an atom loses an alpha particle, it loses the helium nucleus. And so you can see here, I want to show you this. I'm just going to take this out right here. Actually, I think it's easier to do this one because we're going to be practicing with this one in a second. So if we say that uranium-238 undergoes alpha decay, that means the atomic number is going to go down by 2. So the 92 is going to become a 90. And the mass number on top is going to go down by 4. So it becomes 234. Then all you need to do is you need to go look at the periodic table and go, oh, who's number 90? 90 is thorium, right? And so that's how you create a nuclear reaction for alpha emission. Okay, so here's an example. What happens to the alpha emission right here. And again, it loses a big, giant alpha particle helium nucleus. Okay, beta emission. So much fun. So a beta is like an electron. It's much faster than the alpha particle, but also much smaller. So if an alpha particle is like a semi-truck, a beta emission is like a four-door sedan, like a Camry or something like that. So it's less massive than the alpha, which means it can't do as much damage, right? So it has a lower ionizing power, right? But because it's smaller, it can penetrate much better. You've all seen those like cars that are in traffic, right? And you're like in a traffic jam, and those like smaller cars that are like, right? And they're maneuvering, not like great, but they're maneuvering, right? And you're like, where are you going? Because you know they're not going to get anywhere, right? But we've seen them. That's like a beta particle, right? So they can maneuver better. So they're 10 times more penetrating, but only about half the ionizing ability. So this means outside the body, a beta particle is much more dangerous than an alpha, again, because it's 10 times better at maneuvering into you and through your body and into your cells, right? So, but if you got a beta particle in your body and an alpha particle in your body, an alpha would be much, much, much worse. Okay, so when you've got a beta particle, I'm just going to take this off here again because I want you to see how we do this. So what it would say is it would say like thorium-90 undergoes beta emission. That's what it would say. And you're like, okay, so if it undergoes beta emission, well, what does that mean? So that means that the atomic number increases by 1. So instead of a 90, it's 91. And the mass number remains the same. So this stays 234. And then you go look on your periodic table and you're like, oh, who's number 91? Oh, number 91's PA. And that's how you figure out, that's how you write the balanced nuclear equation. And remember, these all have to add up. They have to equal each other. 234 equals 234. 90 equals 91 minus 1. So it's 90 equals 90. They add up together. Okay. And then here's the example of a beta. So again, a beta particle is just an electron. Basically, we're going to call that an electron. And again, remember, it's not exactly an electron because it's emitted from the nucleus, and there are no electrons in the nucleus, but that's a lot larger conversation than we can do in this class. But basically, it's like an electron. Now, gamma. Gamma has the lowest ionizing power. Gamma is just energy. Remember in radiation, you have like gamma rays, X-rays, right? UV rays, like to protect yourself from UV rays, you wear sunscreen. To protect yourself from an X-ray, right? The dentist or doctor puts a lead vest on you. To protect yourself from gamma rays, you become the Incredible Hulk, right? There's no protection from gamma rays because they are incredibly penetrating. So think of gamma rays as like a motorcycle, right? When a motorcycle is going through traffic, you're like jealous, right? Because you know that they're going to just keep going and you're going to be sitting there for 20 minutes and they're just going to keep on their merry way, right? That's like a gamma ray. They can penetrate, but even though they have the highest penetrating power, they don't make that much damage because they don't make as much damage, but they're very, very hard to stop. Like this is multiple like feet of concrete to stop these. There's no loss of particles in the nucleus. There's no change in composition of the nucleus. Again, it's the least ionizing, meaning it doesn't cause as much damage, but it's the most penetrating. And so gamma rays are very bad because there's nothing you can do to stop them, right? If you're at a plane and there's gamma rays, like the further out you are cosmic rays, they're coming straight through the plane, right? You cannot stop them no matter what. So gamma rays generally occur after the nucleus undergoes some other type of decay, and the remaining particles are rearranging. So that's usually what happens in a gamma ray. And you can see here, nothing happens with the mass number or atomic number because there's no particles involved here. It's just straight energy. Okay, now for the really fun one. So a positron. Okay, a positron has a charge of +1, but it doesn't have any mass. So it's like a positive electron, or also called the anti-electron, right? And this is called a positron. It's similar to a beta particle in their ionizing and penetrating ability. So it's similar in their ability to penetrate and their ability to ionize. But when an atom loses a positron from the nucleus, the mass number remains the same and the atomic number decreases by 1. So for example, if I said sodium 11 undergoes positron emission, okay, that means that the mass number doesn't change. So this would stay 22. The atomic number is going to go down by 1. So it goes down by 1. And you go, look, oh, who's number 10? Oh, number 10 is neon. Right? And that's how you do this. And this is a symbol for a positron. And again, the only difference between a positron and a beta particle, or a beta particle is an electron, is you change that to a plus. Where in beta or electron, it's a negative. Okay, so here's an example of a positron being emitted from the nucleus. Okay, now what I think is the coolest one. And when you read more about these, and we're going to talk about these more, and so what's actually happening with the positron is the proton is actually changing into a neutron and emitting a positron, right? So if you actually look at what's happening here, right, the atomic number actually decreases, right? But this stays the same. So if the mass number is staying the same, but we're decreasing the number of protons, that must mean we're increasing the number of neutrons, right? So in a positron emission, the proton is actually turning into a neutron. I'm just going to do N plus a positron emission. Yes, a proton is turning into a neutron, right? And again, the discussion beyond these are so fascinating. We just don't have a lot of time to go into all of the details. Okay, so electron capture, by far the coolest one. So in electron capture, what happens is the inner electrons, like the 1s electrons, get pulled into the nucleus. So the nucleus captures an electron, right? There's no particle emission, but the atom changes, right? So it's the same result as a positron. So it looks the same as a positron, or it's the same result as a positron. And so the mass number stays the same and the atomic number decreases by 1, but it's like literally a proton grabs an electron and together they turn into a neutron. Gotta love nuclear chemistry. Right? And so when you see an electron capture, these are the rarest of them all. You just need to remember the mass number stays the same, right? So 92 stays 92, and the atomic number goes down by 1, right? And then this is the sign. This is an electron capture, which again, it's just an electron in the reactants because it's capturing the electron. So this electron is being captured into this nucleus. And that is an electron capture. Okay, so let's talk about all these because they're like, well, it kind of hurts your head to think about how all of this occurs. Nuclear chemistry is probably the most fascinating type of chemistry that there is. I totally would have become a nuclear chemist, except for the person where I went to graduate school with was retiring and they weren't replacing him. So, and he was the only nuclear chemist expert. But it was amazing. It's so much fun, nuclear chemistry. Okay, so beta emission. So in a beta emission, right, remember, a beta emission that's our electron right there. Right, so that's the charge of an electron. And so when the atom emits the beta particle, the atomic number, I'm going to write this here, the atomic number, I'm not going to use the symbol Z because you might go like, what? I'm just going to say its atomic number increases by 1. Right, that's what's going to happen with a beta emission. And a neutron is changing into a proton. A neutron becomes a proton and emits an electron. Think about that. A neutron becomes a proton, right? And changes it into an electron. And we're going to talk about what's in this neutron that allows it to change into a proton. We'll do that, but not yet though. A positron, remember this, when an atom emits a positron, the atomic number decreases by 1. But because it has 1 less proton after emission. In this case, a proton, again, a proton is changing into a neutron and then emitting a positron, which is the opposite of an electron. And then electron capture, the atomic number decreases by 1, and the proton changes into a neutron. So the proton grabs the electron and changes into a neutron, right? Okay. And then it also emits a positron, which I don't have on here. Okay. So we've talked about alpha, beta, gamma, positron, and electron capture. So it's a lot all in your heads, right? And so this little table here, I don't think your book has anything quite like this. It's everything we just talked about when we talk about alpha, beta, gamma, positron, or electron capture, all in one piece, right? So, and I know it's probably kind of small in your notes, but I suggest going back to the notes and maybe enlarging it so you can continue to refer back to it. Okay, so we have, just so you have this here. And this is going to become very important next week, this NZ ratio. It's going to become very important. This is atomic number. Oh, sorry, this is the mass number. Mass number. Z means atomic number. Why they change, I don't know why they do this. Shouldn't mass number be M and atomic number be Z? I'm sure it's kind of, there's some reason. Okay, so you have here is your beta, which again, you can write it beta 0, -1, or you can do it with an electron 0, -1. Alpha, you can either write alpha 4, 2, alpha 4, 2, or you can write HE 4, 2. Right, either of those. Gamma doesn't have anything. It's just 0, 0. There's only one way to write a gamma. Positron is going to be a +1. That's not what I meant to do. +1, 0. And then you can put a beta, or you can have it. If I write any smaller, my pen's going crazy. I'm sorry. Or you can do it like this. Either or. Right? Okay. So here we go. We're going to apply these. So the question is, what kind of decay and how many protons and neutrons are in the daughter nuclide? Okay, so we count this. So this has 11 protons and 11 neutrons. And then we look at this. So we have 2 protons and 2 neutrons here, right? So that means that the mass number, remember the mass number, is protons plus neutrons. So 2 plus 2. So this is alpha decay, right? This is alpha. This is a 4-2. Why do I keep putting a line there? 4-2 helium nucleus. All right, so if it's a 4-2 helium nucleus, a couple different ways you can do this, right? When you finish this, what kind of decay and how many neutrons? And so if we do this, I don't need to give you all the answers. So if you have 11 protons, I'm trying to figure out a nice way to write this. If you have 11 protons and 2 protons, remember they have to equal each other. So that must mean you have 9 protons and 7 neutrons. So if you have 11 protons, goes to 2 protons, and they have to equal each other, right? Plus 7 protons. So that means this must have 7 protons, right? And the neutrons, it's the same thing. If this is 9 neutrons, and you can either have them separate or you can add them together. I like to add them together. Or, you know, it's going to be here. So if you add them together, you have your 11 plus 9, right? Which is 20. That's the mass number. This mass number is 4. And so you must have, your mass number is 16, or that corresponds to 7 neutrons. It kind of depends on which way your brain works. So we'll try it both ways. Okay, let's try this one. So think about this one for a second. And then what I want to know is how many protons and neutrons are in the daughter. And then we're going to take it up another piece. So try this one. We'll go for the rest of it in just a second. Okay, so we look at this one here. All we have is this piece right here. And so this must be a beta, a beta emission, right? So we've got, and if we look at this, so if we've only lost an electron, what do we have left? So that must mean that we have a positron, or a positive electron, right? A positron, which gives us a daughter nuclide with 4 protons and 5 neutrons, right? So it's going to be okay. I don't know why. Sorry, my pen's not working. I guess I'm not writing anymore. It's not 4 protons, it's 10. It was like 4 protons, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 10 protons, 11 neutrons. All right, our next one. What kind of decay and how many protons? And this one, this is the one that's 4. So you can see this is a positron here, because I have to tell you it's a positron. And so remember that positron nucleus, our protons are going to go down by 1, and our neutrons should increase. Now, if you're like, where are you getting these? You can either look here at positron. It's going to tell you what happens, right? So that's what happens to your mass number. That's what happens to your charge. Or you can look back here also. I think I told you, right? The atomic number goes down by 1 in positrons. And remember, a proton becomes a neutron. So that means our protons are going to go down by 1. And our neutrons are going to go up by 1. Same thing with like our beta emission, right? It's a neutron changing into a proton. So our neutron is going to go down by 1 because our neutron is changing into a proton. And a proton is going to go up by 1. There's a lot of different ways you can think about it, so I hope I'm not confusing you with the multiple ways to think about it. But this is a very much an oversimplification of nuclear chemistry. So there's a couple of different ways we can explain it. Now, an electron capture, your proton is going to go down by 1. Proton becomes a neutron, and your neutron is going to go up by 1. So you can see the result of a positron and electron capture kind of is very similar. It looks similar from the outside, right? It's very, very different from the actual internal what's happening, but they both lose a proton, gain a neutron. So those are the two places you could look for what we're doing right now. In this one, 4 protons, 5 neutrons. 4 protons, 5 neutrons. Again, because our proton went down by 1 and our neutrons went up by 1. Why? Because it's positron. Because, oh, it says positron right here. That's how we know that it's positron. Okay. So let's try this with real nuclear equations. So again, in our nuclear equations, we're going to, all right, everything, nuclear equations, mass numbers, atomic numbers are all conserved. Everything has to balance, right? We just talked about like the top has to balance, the bottom has to balance when we're doing this. And so you can predict it. So let's try a real one. Potassium 40. So potassium 40, positron emission. Positron emission, potassium 40. So first of all, you have to think, what is potassium 40, right? So potassium, remember this is the mass number. That's protons plus neutrons. So potassium 40 is K 40, and then you have to look at a periodic table, 19. Right? So that's the isotope symbol for potassium 40. Then you have to go, what's a positron, right? Remember, a positron is a positive electron. So here's what an electron looks like. A positron is just positive, right? And so remember, when you have a positron, the atomic number, so the protons always are going to go down by 1. When you have a positron emission. Okay, so we figure these two things out. We've got this. So this is what's going to emit. So these are our this is a reactant. I'm just going to put R because my pen's not working, and that's a product. And remember, they have to equal each other. So nuclear reactions aren't really that hard, just because you can see it in the math. So 40, 19K plus something. Or sorry, goes to reactants, goes to our product because it's an emission. 0 positron emission, and you could put E there or you could put a B there. Either of those would be acceptable. So you could have put this. They're the same. And then makes something else. Okay, well, right? That's not so, oh, look, I have it all right here for you. That's not so hard. You have to figure out what they are, but remember, these have to equal each other, right? So if they all have to equal each other, 40 equals 0 plus 40. This has to be 19 has to equal 40 has to equal 40, even though you can't see the 4. 19 has to equal 19, right? And so this must be 18. And then you're like, who's 18? 18 is argon. It must be argon. Right, so here's where we did 40 has to equal 40, and 19 has to equal 19. Well, 1 plus 18 equals 19, and then we just go look and we say, hey, that's argon. And that is our balanced equation. Okay, so now I'm going to give you a minute to try some of these. See how far you get, and then we're going to do these together. So I'm going to give you like 3 or 4 minutes to try these. And again, what I think you should do when you're doing this is go back to one of those slides where I showed you either the big one or the one I said protons go up by or neutrons go down by, vice versa, to do these. So I'm going to give you a minute to try these, and then we're going to go through them together in just a couple minutes. All right, let's try these. Okay, alpha emission, 4-2, right? Alpha, 4-2 helium nucleus. Should just write alpha. Uranium-238, gotta look at your periodic table for these. 238, uranium's 92 uranium. And it's gonna make, it's gonna make a 4-2 helium nucleus. And so remember, they have to add. So 238 has to equal 238. So this is gonna be 234. 92, this one will be 90, because again, they have to add to each other. And then you look at your periodic table, number 90, TH, beta. That's our beta electron, right? That's our beta particle, right? And again, you also could have done this. Same thing. Okay, so we've got neon 24, so we have 24, neon is 10, neon, it's an emission, so emissions are always products, right? And so 0, -1, and I think put a beta there. But again, you could put an electron, either of those would be the same. So this means 24 has to equal 24. And then 10 minus 1, that must be 11, because it needs to be 10 equals 10. See, writing the nuclear equation is not so bad. And then you're gonna go, who's 11? 11 is sodium. Na. Okay, positron emission. Remember, positron's like an electron, but opposite. So, or, let me just fix that for a second. +1 E, or you can put 0 +1 B. Whichever you want. You just need to know that they're interchangeable, so you need to be prepared for either of those. So nitrogen 13, nitrogen 13N. You look at the periodic table, N is 7. This is an emission, right? Emission means these are all products, and it's a beta, 0 +1. I think I put an E on here just so you can see it's a little different. So 13 doesn't change because 13 has to equal 13. And 7 + 1, so this still has to be 7. So 6 + 1 is 7, so we're good. And you're like, 6 is carbon. So that makes carbon. Electron capture, that's a reactant. And remember, it's an electron. So this means we have Be 7 and Be is 4. And it's capturing an electron. So it is a reactant. It's the only one that's a reactant. Now it's the same. 7 has to equal 7. 4 minus 1, so that's 3 on that side. So this side has to be a 3. And 3 is lithium. Right, so there's a lot of different ways you can remember this. You can either remember like what I said, like the increase in protons and neutrons, or you can just do like what I do. I like to memorize the particles and then just use adding and subtraction to figure it out. Either of those ways are going to give you successful answers each time. Okay, so I have these super pretty here for you. And I used E's instead of beta particles for this one. I used helium here. So remember, this is the same thing as this. 4-2 alpha. This is the same thing. It's a beta. This is the same thing as this. And this is the same thing as this. Those are equal to each other and interchangeable. Okay, so I think we'll finish there.